All right, so today we're going to continue our discussion following our last lecture. At the end of our last lecture, we briefly mentioned what we mean by weak consistency and strong consistency in statistics. So in short, weak consistency is about, let me turn the light. Weak consistency is about the convergence of an estimator to a parameter in probability. And here the estimator is considered as random because the estimator relies on a random sample. So that's our basic assumption in statistics. A sample is random. And this parameter in the frequentist paradigm is considered as fixed, a constant. So we have a sequence of random variables or random vectors converge to a constant or a constant vector or a fixed vector. That's weak consistency. And strong consistency is actually about convergence almost surely. So now I have a question for you guys. Why do you think in statistics, most of the time, we only care about or we only talk about weak consistency? This is the common one, and we are pretty happy about it. Why is that? Do you have any ideas about this? Have you ever thought about it? Now you know what is convergence in probability and what is convergence in almost surely. Then why the first one, the weak version, is good enough? Think about their differences and think about the counterexamples we have given you. If you have any thoughts, feel free to unmute yourself and speak up. Okay, here's my answer. So maybe you can offer some new insights, but this is what I think. Okay, so in statistics, why this is so common, the first version, is because we actually only have a fixed n. So in statistics, given a sample, n is fixed. So you know the sample size. So basically you only care about, okay, given a large enough sample size, is my estimator close enough to my parameter? So in other words, given an n, you want to look at this probability. That is my estimator within an epsilon neighborhood of my parameter? And does this thing hold with, so maybe I write it another way. So I want to have this within the neighborhood. I want this to hold with high probability. This is what I care about. And of course, on the opposite side, I want this to hold with low probability, right? So that's good enough for me. And for the almost sure convergence, what does it mean? As I said, it means that the realization, every realization will converge. But that will actually mean you have a realization of, say, you have, so I'll use lowercase theta 1 hat to theta n hat and theta n plus 1 hat and so on. So I will want this particular sequence to converge to theta. So this is like realization. And so that will actually have the n actually grow. So you obtain a realization of sequence. But as I said, in statistics, we often only get one n, a particular n. That's why this convergence is not actually realizable. We will not grow n. So that's why this one is less relevant, but this one is more relevant. But still, as we said, we can actually go from almost sure convergence to convergence in probability. So whenever it's easier to prove the stronger version, we will go here and then use it to prove the weak version. And the weak version is more relevant in our statistical analysis. That's my answer in short. But you can think about it and see if you'd agree with me or don't agree with me. Okay, so related to this, right? So this is the general discussion about what we mean by consistency. But related to this, a very important result is what we call law of large numbers. So in law of large...
Hi, Professor. I have a question here. So when we talk about the almost sure, like this series of like theta hat 1, 2, for example, n to n plus 1, we just adding one more data, right? And, to preserve all the previous data we collect.
Actually, no, that's not the case. So basically here that's a very good point, and that's something I mentioned briefly before, but I'm going to clarify again. So here we're basically saying that when we have the realization, so each random variable in the sequence, say theta hat n plus 1, they will have their individual realization. And we don't yet specify the dependence between theta hat n and theta hat n plus 1. So we didn't specify anything like that. And if you want to say, as you said, we just like a sample mean, right? We add one more data point, calculate mean again. That's a very strong condition on how the sequence will be like. But in general, when we write this down, we don't specify the dependence at all. We just want to say, okay, no matter what the dependence is, for every realization, the realized sequence must converge. That's the definition of almost sure convergence. But how to achieve that, whether you want to specify the dependence in the sequence, that's a separate question.
Okay, so when we talk about consistency, we do not assume like
we didn't assume.
Okay, got it.
Yeah, that's the magic of law of large number. That's my next thing. Yeah, so the special case we call law of large numbers, right? LLN, that's the acronym. So here, the theta hat n is actually what we write as xn bar, right? That's actually 1 over n summation xi. Okay, and here you see in this definition, so Kangcheng, what you just said actually applies here, because you see when we have this theta hat n written as this, even though the xi's are all random, but you see their realizations are coupled, right? So basically you see here, okay, let me call this sample mean. This is what we call sample mean. And why do I say they're coupled? Because you see theta hat n is actually what? It's determined by x1 to xn. And theta hat n plus 1 is determined by x1 to xn to xn plus 1. And when we talk about realizations, we're actually talking about realization of these random variables that will give us the realization of this particular theta hat n or theta hat n plus 1. So that's why you see they are naturally coupled. So in this law of large numbers, yes, they are. But in the general discussion of almost sure convergence, that's not. That's the clarification. Because this is just because we're defining this as an average. And so where you see, when I get a realization, right, this is realized n numbers. And these n numbers is also the realization here. So what's changing is the addition of the additional one. So that's just a special case of theta hat n. I hope this clarifies. Okay, and yeah, so the law of large numbers is regarding the relationship of the sample mean and this population mean. So here, this theta is actually what we read as mu, and that's the population mean. And it's actually defined as the expectation of every xi. So in other words, we are assuming the xi's to have the same mean. So that's the typical assumption in statistics. Here, let me write it down. This condition is that the xi's are IID. IID is a very strong assumption, but it's the most common one you see in statistics. Identically and independently distributed. So being identically distributed, every xi comes from the same distribution. Independently distributed means that they are independent of each other. So with this assumption, then you can have this law of large numbers, but still there is some requirement. So the very important requirement for law of large numbers is that the absolute value of xi's expectation must be finite. So you cannot violate this condition. Otherwise, the law of large numbers will not hold, right? It doesn't have a finite mean, in other words. You need to have this mean finite. And this is actually stronger. When you have the expectation of absolute value finite, then the expectation of the not absolute value version of the random variable must be finite. So this guarantees this to be finite. Okay, let me write this. And then you will have a finite limit. So then we have two versions, weak law of large numbers. This one says theta hat m converges in probability to theta. And strong law of large numbers says almost surely to theta. But you see, even though we stated two versions, but the strong version implies the weak version. So that's why once we can prove this, we can prove the weak version without a problem. And for the strong law of large numbers, there are very complicated proofs and also an elementary proof. So, but for the elementary proof, it just means it uses elementary techniques, but it's actually pretty lengthy. So if you're interested in that, we have made a note, I think, give a reference in the notes. Okay, so that's all I want to say about the convergence. But you know, as I think maybe Zach or someone mentioned before, there are some interest about the concentration, about concentration of estimator around parameter. Okay, and so in statistics, there are actually names for this. So this is called just a side note, okay? This is called large deviation theory. So when people talk about this, not the large sample theory we're going to talk about later. So when we say large sample theory, it's actually about asymptotic distribution mostly. So that's our main topic of this class. But for large deviation theory, it's actually mostly concerning this thing. So this probability, as I said, is largely concerning this quantity. That is, what is the probability that my estimator is away from my parameter by epsilon? So it's actually trying to control this so-called violation quantity. You can think about it that way. So this is like a violation probability. So which means that, okay, the estimator is not behaving well. And we want to control this. And also large deviation theory want to give this a rate. Oh, sorry, my bad. Theta hat m. Want to give this an upper bound, and the upper bound depends on n. So we want that as n goes up, the upper bound should go down to 0. That's the good property we will desire. So this large deviation theory is trying to give it an upper bound that goes down to 0 as n goes infinity. And also we care about the rate. So the rate is important because if it goes down fast, that's better. If it goes down slower, that's not good. Okay, so for this one, we actually have several interesting inequalities we may use. So here, because this is not the focus of this course, I'll just briefly preview them or review them a little bit. So there are some important inequalities. The first one and the most basic one is what we call Chebyshev's inequality. I think many of you have seen that before. for Chebyshev's inequality, you are basically giving an upper bound based on the second moment of a random variable. So in other words, it's not about theta hat n, but I'm just going to use a random variable x, okay? X is a random variable, and mu is its mean. So here, this quantity, the Chebyshev's inequality, can actually, maybe I'll just use greater or equal than. That's the more common form. So this can be bounded by what? Sigma squared over t squared. So here, the mu is expectation of x. Sigma squared is the variance. So it's actually expectation of x minus mu squared, or we write a variance of x. That's the Chebyshev's inequality. So you see, it's going down to 0 at what rate? At 1 over t squared. And here, I'm not talking, here the n is not appearing because you see, here I'm not having n here. But if you have sigma hat n, if this is sigma hat n, then the n should appear somewhere here. Because here, if you imagine this x is the sample mean, then there's a denominator n, right? And the denominator will go to the variance, n will go to the variance, the denominator, and it will go down here. So n will appear here. So then you can talk about the rate of n. But I'm just giving the general form, so I didn't write it out. And another very useful result for talking about sample mean is what we call Hofston's inequality. So for Hofston's inequality, it gives you a tighter bound. So basically, it's actually very flexible. You only have two requirements. Here it's about sample average or sample sum, right? Because average is just the sum divided by n. So we can just talk about sum and then divide that by n. We can get an average. So in Hofston's inequality, here, we just need to require x1 to xn to be IID, again, an IID result. Each one has 0 mean. We simplify the problem a little bit, and we have every xi having a lower bound and an upper bound. So ai less equal than xi less equal than bi. So we get this upper bound and lower bound. And then we can bound the sum of xi. I from 1 to n greater or equal than epsilon, okay? Then this can actually be bounded by a very interesting quantity. So it's actually of this form. So in the denominator, it's exponential to the power t epsilon. And note that this t is a constant, and actually this can hold for any t positive. Okay, and in the numerator, what we will have is a product, I from 1 to n, exponential to the power t squared times bi minus ai squared over 8. This is the general Hofston's inequality. And then you can see, you can optimize the right-hand side by finding the value t to minimize it, right? Because we said this holds for any positive t. So therefore, you can always find a t to minimize this, and that's the tighter bound. So in other words, the tighter bound, and that's what we actually use in practice, is to find a minimum of t greater than 0 of this bound. So that will be the thing we will use. In particular, the Hofston's inequality is very useful for what? It's very useful for bounding the sum of Bernoulli random variables. Because for Bernoulli random variable, each xi being Bernoulli means that its lower bound is 0, upper bound is 1, right? So you can plug in ai for 0, bi for 1. Then you see this numerator here, you will actually get t squared over 8. Because you multiply them by n times, then they will become exponential to the power n t squared over 8. Then that's the numerator, that's the denominator. You can do the optimization for t, and then that will give you a lower bound. Okay, so that's the result. So if Xi's RIID Bernoulli P with probability P, then actually the Hofston's result will give us, so it will give us this very nice result. That is, it can give you the deviation of the XM bar, the average of those Bernoulli. Let me see. Sorry. Yeah, the average of those Bernoulli minus P. This thing greater or equal than epsilon can be upper bounded by 2 times exponential to the power -2n epsilon squared. So you see, this is a very nice result because you see the deviation is decreasing in the order of exponential -m. So it's decreasing very, very fast down to 0. So that's a very nice bound for Bernoulli random variable. And that's a result of Hofston's inequality. Okay, that's it. And furthermore, you see another very useful thing is what we call the Bernstein inequality. So for that one, it's also trying to give us an upper bound, and it's also regarding exponential decay. So here I'm not going to talk about that further, so you can check it out. So, but this is also another thing very useful. It's called the Bernstein inequality. So for this one, what we basically use it is also, okay, the condition is x1 to xn IID still, and 0 mean still. And here we basically can give it like 2 symmetric upper bound and lower bound. So the upper bound is m, lower bound is -m. And you can still use, so you can still have an exponential upper bound for the deviation. But the difference is that it has a slightly different form from that of Hofston's inequality. So largely similar, but technically slightly different. So sometimes using the Bernstein's inequality can give us a tighter bound than the Hofston's inequality. So that's why we have this. But I'm not going to talk about this in detail. But you already get the sense what we mean by the large deviation theory. Yeah, these are based on those inequalities. So coming back to our main focus in this class, when we say large sample theory, also, as we said in the first class, some people say it's asymptotic theory. We focus mostly on the distribution of a statistic. So this is what we call the statistic of sample size n. We focus on its distribution, and we say asymptotic distribution. That's the focus. And we want to derive this distribution so we can approximate its behavior, the values this statistic can estimate or statistic can take as we vary our random sample, right? We change our sample from one sample to another sample to another sample, so we can get infinite values of this statistic or estimator. Then what will be those values distribution? And so hopefully as n gets very large, we can use the asymptotic distribution as an approximation for this distribution. That's the purpose of this class. Okay, so we want to talk about, so for that purpose, the central topic is what we call central limit theorem. So central limit theorem is the basis of all the asymptotic distribution we're going to talk about later. So this is so important, and we will talk about this very soon. Okay, but I'm still trying to get back to my notes to follow the order so you will not get confused. Before we talk about central limit theorem, so as a follow-up of the consistency, okay, we just talked about consistency. There is a very, very important estimator that we cannot ignore. So back to consistency. Back to consistency, we'll talk about the general form. But here, we want to give you a special estimator. That's what we call empirical distribution function. Okay, so you will actually see some people call this EDF or ECDF. You can see both. So ECDF, it means empirical cumulative distribution function. And some people just ignore C, just call it EDF, but they're the same thing. So essentially, you see, we define the CDF, right? The CDF is defined based on a distribution. So let's say that we have x1 to xn. They are IID from the same distribution F. This is what we mean by CDF. And then the CDF we defined in the first lecture for a particular value or vector in the domain of those random variables is defined as the probability that each random variable from this distribution is less or equal than this, right? That's how we define the CDF. But what do we mean by empirical? Empirical means that we don't know what this is, but we can estimate this from our sample, this x1 to xn. Okay, you can imagine that here we have one set of realization, one for each xi, then they become numbers. So given the n numbers, can we find an estimated function for the CDF? That's what we call empirical CDF. But how do we do it? You know, whenever the trick in statistics is that whenever we want to use our sample to do something, we mostly rely average. We want to get some average about the n numbers. And the average itself, sample mean or sample average itself, is an estimator for a population mean or expectation. So therefore, in order to connect the two things, we first want to write out our population quantity as a form of expectation. And here, the probability can be written as what? As an expectation of an indicator function, right? And here we're going to do that. So this can actually be written as expectation of the indicator that xi. That's it. Now it becomes straightforward. By empirical, we will replace this expectation by average. So that's our ECDF. So in the notes following the Ferguson book, I use the notation FNX to mean the ECDF. But I want to make a note that in some other books or in many papers, you will actually write it as FN hat X. So the hat is trying to emphasize that, okay, this is an estimator. This is estimated from our sample. So leaving the hat on is more accurate. But here we drop it just for notation simplicity because we're going to write it again and again. So dropping the hat makes it simpler. But I want to make sure that you know they're the same thing. Okay, for this empirical CDF, then, as I said, we use sample average to estimate expectation. Then here, it becomes the average 1 over n, summation I from 1 to n, indicator xi less or equal than x. Then it becomes natural. That's the ECDF. And what does it mean actually, you know? So empirically, when we calculate this, right, we are basically looking at our n numbers. And for each number, we compare it against this potential value x. X is any value in the domain of my random variable. Say, if my x1 to xn follows are from the real line, then this x can be any real number. Then I compare each number to the real number and note whether it's less or equal than or not, right? Then I count the proportion of my n numbers that are below this real number. That's the empirical CDF. So by this definition, you see the empirical CDF is still a valid CDF. It's actually between 0 and 1. And what it actually does is that it's actually placing a probability point mass 1 over n at every xi. This is essentially what it does. It's a discrete distribution by nature, and it places the same mass on every observation. That's the empirical CDF. And furthermore, is it random? Looking at the definition, is it random? Yes, because every xi is random. That's why that makes the eCDF a random quantity. Okay, so next, given our law of large numbers, what can we say about this and this? What can we say about the relationship between the fx, fn, given any x, and f at the same x? Can we say anything about that by the definition, by the law of large numbers? Yes, right. So given the strong law of large numbers by SLLN, given any x, we would have fnx converges almost surely to fx. This is a direct application of the strong law of large numbers. But are we done? Actually, because the CDF and eCDF are nice, they actually have two important properties as a CDF. First, they are bounded below from 0 and above from 1. So they're between 0 and 1. Second, they are right continuous, right? We talked about that. They're right continuous. So these two properties are very important, especially the boundedness. That can actually give us a stronger result. We can actually say about the convergence, not just for a particular x, but uniformly for all the x. So we can talk about uniform convergence. So this is just what in mathematics, this is called pointwise convergence. That is, for any x, we have convergence, but the convergence may not be uniform. What does that mean? So here is an example saying that pointwise convergence is different from uniform convergence. We're going to give you a review to some of you or definition to some of you. So this direction doesn't go, but this direction goes. So what's the difference between those two? Okay, so by definition, pointwise convergence means that for given x, we have fn x converge to fx. So, okay, maybe I should use the general notation, this one, f and f, sorry. Yeah, the reason I want to do that is here I want you to forget about the randomness, etc. Just think about a sequence of functions, okay? So in this box, we don't talk about random variables, we just talk about a sequence of functions. And here, this says that I have a sequence of function lower fn converges to another function lower f, but this convergence is for any particular x. So in other words, you see, here we have the, we would have something like this. So basically, the definition here is that given any epsilon greater than 0, okay, and then we can find an n index in the sequence, and this n actually depends on this x, depends on the particular value you look at. So such that you see for any n greater than this nx, we would have fnx minus fx less than epsilon. So the key thing here is that we have to let the index change depend on this particular value we evaluate those two functions. That's pointwise convergence. But for the uniform convergence, what it's about is actually this. It's actually about the soup over all possible x that this fnx minus fx goes down to 0. So in other words, the convergence is uniform for all the x, not for a particular point x. And so by using the epsilon definition here, this n actually does not depend on this particular x. It's a uniform n. So in parallel, it will be written as any epsilon greater than 0, there exists n such that for any n greater than big N, we have the soup x fnx minus fx. The soup will be less than epsilon. So you see the difference. So this is a much stronger requirement. This is a looser requirement, right? So this the analogy is the continuous versus uniformly continuous. So it's very similar to that concept, that difference. Okay, and a counterexample is always a good thing to know about, right? To understand the difference. A counterexample I'm going to give here, again, this has nothing to do with randomness. It's just to understand the difference between pointwise convergence and uniform convergence. Let me define fnx to be x squared over m plus x. And let me define fx to be just x. So you see, the pointwise convergence is very obvious because as n goes to infinity, given x fixed, as n goes to infinity, this first term will go down to 0. Then this converges to this, right? That's very natural. So basically, we can see that given x, this fnx minus fx is just x squared over n. And for sure, this go to 0 as n go to infinity. But look at this. If we take soup over x of this quantity, fnx minus fx, once we take the soup, it becomes soup x, and this is for all the x over the real line. And you can clearly see this is not bounded, right? Because the soup of x can clearly be larger. We can pick, for example, we can pick x equals n. Then the soup is larger than that particular value of x. So we can clearly see that this is bigger or equal than n squared over n. So by doing this, I'm just letting x equal to n. And that's what? That's n. And it does not converge to 0. So this is a typical case where we have pointwise convergence, but not uniform convergence. Okay, after such a long discussion about this concept, right? What I want to say is that coming back to the empirical CDF. So back to the empirical CDF to Fn. We want to say that we have a stronger result, more stronger than strong law of large numbers, because strong law of large numbers only talking about pointwise convergence. Given an x, we have almost sure convergence. But here I can tell you that we can make this stronger by letting the convergence be uniform. So we actually can have uniform convergence almost surely. Not just pointwise convergence almost surely, but uniform convergence almost surely. Okay, what does that mean? Here, again, a very useful review. Almost surely, when we say this, we mean that an event occurs with probability 1. That's what we mean by almost surely. And here the event is that we have uniform convergence of eCDF to CDF. That's the event. So therefore, what we mean by here is the probability that sup x of f and x, that's the ECDF, minus the CDF, the sup over x, this is going down to 0 as n go to infinity. This whole event has probability 1. That's what we mean by uniform convergence. And you see, this is a stronger result, right? So as a comparison versus, SLLN, what we write above is just that the probability of this minus this go to 0 as n go to infinity for any x is 1. This is the meaning of the strong law of large numbers. So I'm just writing it out in another way based on the definition of almost sure. Okay, so you see here it's about this event for a particular x that holds with probability 1. But here we are changing the event inside the probability from pointwise convergence to uniform convergence. And so this stronger result actually has a name. This one is called Glivenko-Cantelli Theorem. So that's the name for the stronger result. The almost sure convergence of uniform convergence. That's basically Glivenko-Cantelli. And so for the proof, which I think I'm going to skip, you can actually check the notes. It's not very difficult. The trick we utilize is actually the boundedness of these two CDF. Because their values are between 0 and 1, then I can divide that value range 0 to 1 into small intervals. I can divide them into many intervals based on my size, right? Based on a given epsilon, let's say the epsilon here, given epsilon, I can divide that 0 to 1 range into many, many intervals so that within each interval, the function values do not differ by epsilon. And given those interval definition, I can find their corresponding values for Fn and F. So that's the value whose function value will fall into the interval. And then because the intervals are defined and they're finite, there are a finite number of them given an epsilon, I can apply the sup. The sup over a finite number of things is not difficult. That becomes max. And then I'm almost there. So it's just to utilize the range 0 to 1. And also, because of that 0 to 1 range boundedness, that can allow me to generalize pointwise convergence to uniform convergence, because the uniform is only going to take over a finite number of things by changing sup to max. That's the intuition behind the proof. But I think I'm not going to really write it down. So you can check the notes. If you have questions, you can let me know. But I think it should be understandable. Okay, that's the Glivenko-Cantelli. It's a very nice result that makes you realize, okay, we do have very nice properties about the ECDF, okay? And furthermore, for the actually we know this holds with probability 1, right? So this is going down to 0 for sure. But what if we talk about its, this is like the almost sure result, right? This event held with probability 1. How about the with high probability result? So similar to convergence in probability. So that's another question. So how about this thing? The probability that sup x f n x minus fx greater than epsilon. How about this? If you want to talk about a large deviation, can we actually give this thing an upper bound? Yes, we can. actually, we do have a nice upper bound for this quantity, the large deviation. It's written similar to what we just did. The Hofston's inequality for binary variable, the upper bound has the same form as that. 2 times exponential to the power 2n epsilon squared. So we can actually get a rate, okay? This soup is going down to 0 at this rate, exponential negative n rate. So that's very fast. And for this one, this also has a name. So I'm not going to write down the full name, but you can check it. This one is in short called Dkw Inequality. So I hope this can make you realize that when we evaluate like an estimator, we have multiple aspects. We already talked about 3 aspects, right? As a summary. So 3 aspects, 3 asymptotic aspects, or you can think about them as properties, desirable properties to evaluate an estimator. Estimator, let's call it theta hat n, depending on sample size. The first one is, of course, consistency, right? So does my theta hat n converge in probability to theta? That's the first thing. And sometimes it might be easier to show via almost sure consistency. So maybe it's easier. Maybe easier to show this almost sure convergence as a first step. Then you will have the convergence and probability directly. But this thing is only about, theta hat n minus theta greater than epsilon. It's only about this fact. It doesn't give you an upper bound or the convergence rate for this large deviation. So that's why the second aspect is to look at the large deviation. That is, what is the upper bound of this, right? So we want to find this. And this upper bound depends on n. So yeah, so that's the second aspect. And for this one, we need to utilize those inequalities. That's the second aspect. And the third aspect is the focus of this class, asymptotic distribution. So usually, we cannot directly say what is the asymptotic distribution of an estimator without multiplying it by some growing constant. So for example, in the central limit theorem, which we will see next, we will actually derive the asymptotic distribution of the sample mean. But we have to, do this. Root n times xn bar minus mu. So we will show that this asymptotic distribution, this is converging in law to a normal or Gaussian distribution with mean 0 and covariance matrix sigma. So you see, this is what we will do, but we're not saying it's the asymptotic distribution of xn bar. We're saying it's xn bar centered and multiplying by root n. And this root n is growing to infinity as n goes up. So it's like a counteracting the diminishing of this xn bar. Why do we need that? The reason is that we know here by strong law of large numbers, xn bar converges in probability to mu. So in other words, xn bar minus mu converges in probability to 0. So we know converging in probability to a constant implies converging in law to a constant. So we can say xn bar minus mu converges in law to 0. So it's reducing, its distribution is reducing to a point mass. There's no shape, right? So to counteract that diminishing effect, what we do is we multiply it by a constant, increasing constant. So basically, after just counteracting, we can stabilize the distribution. So this is the key fact for this whole asymptotic theory. So to summarize what I said, that is xm bar minus mu, just by itself, it actually converges in law to 0. It's a point mass. And this is by law of large numbers. That's not useful, right? It doesn't give us any useful information. But multiplying it by root n, we get a very meaningful distribution. That's nice. And that's the focus of this, the later part of this class. We'll focus on the aspect 3. And then another question you might wonder is, why do we care about it, right? Why do we need asymptotic distribution? The reason is that it can give us a lot of useful information about confidence intervals, about hypothesis testing, right? So those are very useful information we as statisticians care. So this one describes how this statistic in this form will take values with different frequencies. So that one can allow us to evaluate what we can say about our particularly observed value for the statistic. Okay, so useful for hypothesis testing and confidence interval construction. Okay, great. So now let's come back to our first major topic about asymptotic distribution, central limit theorem. So central limit theorem is actually built upon the Levy's continuity theorem. It's very useful for proving the central limit theorem. But before going there, I want you to give you some very interesting results about characteristic function. Okay, so we used characteristic function to help us prove it. And the first thing is like the review of characteristic function. So let's write this phi x, okay? So in our undergraduate class, because I have taught the 100B before, and in 100B, we didn't ever talk about characteristic function. We only talk about moment generating function. So you can consider the moment generating function to be like a special case of this. So this is more general, that is more specialized. So some distribution, not all distributions have moment generating functions, but all distributions have characteristic functions. So that's very, very, very important, because you can see naturally, we know some distributions don't have moments, right? Like the Cauchy distribution. That doesn't have any moments, but still it can have characteristic function. So this exists for any distribution. Okay, this is not necessary for moment generating functions. Okay. And also another interesting interpretation of this is that if the distribution is continuous, that means it has a probability density function. In that case, the characteristic function can be regarded as the Fourier transform of the density function. That's very important as well, because it basically means that you can present, you can show your distribution in the form of characteristic function. It just itself defines a distribution. And furthermore, nice property is that you can actually evaluate it at values. Okay, so here, let's review this again, right? This is the definition of the characteristic function. Then by definition, we can clearly see that if we evaluate at 0, okay, we will get what? 1. That's what we'll do. And what else? If we take its derivative, first order derivative, by our last lecture, we used the notation by writing a dot above. So taking a first order derivative, and then we evaluate at 0, then we can trivially see that it's actually expectation of x, and that's mu. So that's the first order derivative. But no, last time we said, okay, this is defined as a row vector for the first order derivative. So if your mu is defined as a column vector, then you need to put a transpose here. Okay, that's just a technical stuff to pay attention to. But here you see the reason we can do it is because we can exchange the differentiation with expectation because the function is very smooth. We can put a differentiation inside, then we can get x down here and then it, right? So then basically, when we evaluate at 0, then this term becomes 1, it becomes 0. Oh, sorry, my bad. Sorry, this is actually 0. My bad. Yeah, I got confused myself. Yeah, this is actually 0. So we can trivially show that. And this is a 0 vector. Don't forget about that. It's a vector 0. And lastly, about second order derivatives. So for a characteristic function, we can actually show that it's negative covariance matrix. Okay, and the covariance matrix is defined as negative, we can write variance of x. So when x is a vector, then this is d by d. It's a d by d matrix. So therefore, these are very useful properties of the characteristic function. And furthermore, a characteristic function is very, very useful for linear transformations of a function and the sum of independent random variables. Okay, so basically we can have this nice property that is if we do this ax plus b transformation for the characteristic function at t. Okay, and then we can see what? By the definition, it's expectation of exponential it, now it's ax plus b. So we can see this is equal to exponential itb, get it out, and multiply the expectation of exponential itax. So this is actually itb times phi of x evaluated at at. So we can clearly see that we can perform the linear transformation of the random variable and then still have the characteristic function of the transform variable based on the characteristic function of the original variable. That's the linear transformation. And furthermore, another useful property, I'm just going to write down here, is that if you have probably next page. Okay, maybe I'll just turn the page. So that another very useful property is if you have independent x1 to xn, then phi of summation xi at t. You see, I can write it out as expectation exponential it summation xi. Then I'm going to use the independence to write the expectation of a product as product of expectations. So that will give us expectation of itxi. Then that's the product of phi xit. Okay, And that's another very useful thing. If x1 to xn are IIDs, which means that they have the same characteristic function, then I can further simplify this as phi of x1t raised to the power n. Okay, we almost have all the components we need to prove central limit theorem. But furthermore, before we can actually do it, we need another useful fact, that is the Taylor theorem, which is just like Taylor expansion we learned from calculus. That can also help us, that will help us to prove the central limit theorem here. Okay, so why do we need that? Here, for the central limit theorem, in order to prove the result, we actually utilize Taylor expansion so that we can expand the central limit theorem around zero. The quantity in the central limit theorem for the characteristic function around zero. That's a key fact we need. Okay, so I'm just going to directly prove the central limit theorem and then we'll end this class. And during the proof, we're going to utilize the Taylor's theorem. So we'll use it when we'll talk about it when we use it. Okay, so now finally, central limit theorem, the statement. So we have x1 to xn. We're going to prove the vector form. Okay, they are IID random vectors with mean mu. So the mu is d-dimensional and covariance matrix sigma. Okay, that's d by d. And one thing that's very important is that we want this covariance matrix to have every entry as finite. Okay, so finite entries. That means every variance and every covariance in the matrix is finite. Then we have root n, xn bar, the average sample mean minus mu, converge in law to this multivariate d-dimensional normal distribution. So I put d here, 0 and sigma, and this 0 is also d-dimensional. That's the central limit theorem. Okay, and to prove this, we're just going to use Levy's continuity theorem to show, okay, the characteristic function of the left-hand side is convergent to the characteristic function of the normal distribution on the right. That's it. All right, so let's do the proof. So first of all, we are going to write this left-hand side based on the average. We're going to expand it, okay? So this is equal to, this is equal to root m times 1 over m summation I from 1 to m, xi minus mu. Basically, this part is equal to this part, just an average. And then, you see, I can cancel out root m from the denominator. So I get 1 over root m. Okay. So therefore, you see that by writing out the characteristic function of the left-hand side, right, at t, at any value t, you see, it's basically a scaling of this quantity. So, sorry, I'm going to write it one step further. So it's a scaling of the sum right? This is like the b, the ax plus b. This is the a scaling. So I can get a inside, right? So this will give me, based on the property we just said, sum xi minus mu t over root n. I'm moving a inside the function. And then I'm going to use the IID property, right? These xi minus mu, they are all IIDs. I'm going to use the IID property, and I will write it as the characteristic function of x1 minus mu evaluated at t over root n, this function to the power n. I'm using the property I just did right now. Then what is this, right? I just need to get this thing in the base. Okay, so for this characteristic function xi minus mu evaluated at t over root n, I'm going to apply Taylor expansion here. So this is the multivariate version of Taylor expansion. So I'm going to have it expanded at 0. Sorry, xi minus mu. So I'm going to just write this just for simplicity. Okay, I'm going to write this as phi t over root n. Just omit the sub-index, the subscript, just for simplicity. So I expand it at, so this is just that. I ignored it. Okay, this is just a 0. I've expanded at 0. And I also go one term for the first order derivative. That's phi dot at 0 times the difference between the two things. That's t over root n. That's the first order. I'm going to keep it. And because, you know, this, if you recall from our last page, you see, here we have this at 0. So that's why the first order derivative is not so meaningful. We'll just have a 0. So we want to go for one more term to the second order derivative to get a covariance out. Okay, so that will be dot at 0, the second derivative. But what is the Taylor expansion there? Okay, so that's something in the notes. It's like a mean value theorem, if you still remember that from calculus. We're going to write the second order term by the mean value theorem. So essentially, here we are going to write it as this. So in the multivariate version, it's actually t over root n transpose, okay, t over root n transpose times, in the middle, we would have a double integration from 0 to 1, from 0 to 1, and it would be v times the second order derivative evaluated at u times v times the value t over root n. And then we have du dv. That's in the middle, okay? And we're not done yet, times t over root n. Okay, so this is what? This is basically a multivariate mean value theorem applied to the second order derivative term. That's basically it. It's just like here, we don't go further. We don't go the expansion further. We stop at the second order derivative term. But here, instead of evaluating the second order derivative as 0, we are taking the average over what? So you see, u is a value changing from 0 to 1, a scalar. V is a value changing from 0 to 1, scalar. And we are doing this double integration. And this is t over root n, t over root n. You see, in the one-dimensional case, this is just their square, but this is a multivariate. So we have to do the transpose times itself. And in the middle, we would actually have a matrix form as this. So this is also in the notes, and we call this Taylor theorem. So Taylor's theorem. in the notes. So I will leave this to you for reading to actually understand why this holds. As I said, you first need to verify to understand the multivariate mean value theorem applied to the first term. That's also in the notes. Once you have that, then you can do that on the first order derivative, so you can get a Taylor theorem, which is about the second order term. That's it. Okay, so now we have written this, right? This term we care about in the base as this. And it's actually very good because we know by the property of characteristic function we talked earlier, this first term is 1. This term is 0. So we are left with 1 plus something. And this something, is divided by n because a root n here, So it's 1 divided by something. Well, sorry, it's some numerator divided by n. So let me quickly summarize this part. And we will actually have, so basically what I said is that this phi x1 minus mu evaluated at t over root n is simplified as 1 plus something. And here the something is divided by n. In the numerator, we actually have T transpose times the double integral. Okay, in the double integral, it's V times the phi second order. Again, this is x1 minus mu. I'm writing back the subscript. U times V times T over root n. du dv. Okay, that's in the middle. It's a matrix times T. That's it. And we just need to actually, and this, basically this is a matrix, but T transpose times a matrix times T. T itself is a d-dimensional vector here. We get a scalar. So another very useful fact is that, let's call this A. Okay, let's call this as 1 plus A over M. A is a constant. So another, and this A doesn't, this A is a constant, sure. And maybe let me put the N here, subscript N, because there's an N inside, so A does change with N. So using this notation, then you see the characteristic function I'm interested in showing for the central limit theorem. This thing evaluated at T now becomes 1 plus an over n to the power n. And one nice thing about this is what? We actually have an interesting result from our calculus. So that is, okay, the focus. Okay, so what is that? So basically, what we have from our calculus is that, so if an is going to a constant a as n goes to infinity, then this 1 plus an over n to the power n would converge to exponential a. That's the fact we're going to use here. So we're going to utilize this fact to prove what this is convergent to. This is what we want to find. Okay, then let's revisit this part. Okay, let's revisit this part to see what is convergent to. T transpose 0 to 1, 0 to 1. V U times V times T over root n. du dv and T. Okay, so when n goes to infinity, only this term is changing. So basically, u and v are between 0 and 1. They're constants, but this root n is going to infinity, so this ratio is going down to 0. So we would actually have, because it's a very smooth function, we can get a limit inside the integration. So this will actually converge to T transpose 0 to 1, 0 to 1, v 0, du dv t. And we know by the property of characteristic function what this is. This is equal to negative sigma. That's what we just said before. Because you see, when this is a negative sigma, has nothing to do with u or v. I get it out of the integration. So I'm just getting double integral of v du dv, and that's 1/2. So therefore, the limit is equal to negative 1/2 T transpose sigma t. That's it. So finally, I conclude that the characteristic function of the central limit theorem left-hand side, this is converging as n goes to infinity to exponential to the power negative 1/2 T transpose sigma t, which is the characteristic function, of this multivariate Gaussian with mean 0 and covariance matrix sigma. So we're done. So we showed that this characteristic function of this root n times x n bar minus mu is convergent to the characteristic function of the normal distribution, and that proves the central limit theorem. So ultimately, the proof relies on Levy's continuity theorem and also very important characteristics of the characteristic function. So yeah, we just finished the central limit theorem. I hope that you think it makes more sense to you now, because I know everybody learned this from undergraduate class, but we didn't actually prove it in undergraduate class, I think. So here maybe some of you have seen the proof based on moment generating function. So technically wise, it's pretty similar, but as I said, moment generating function is more restrictive, but characteristic function is more general. So that's all for today. And yeah, I hope everyone can really think about the intuition we give in this class, why we really need to learn those stuff, right? They're actually useful because they are actually, central limit theorem can give you the asymptotic distribution of many useful statistics. And that can give us the ability to do hypothesis testing and confidence interval construction. Okay, so see you on next Tuesday. And please don't forget, for those of you here, don't forget about the homework due tonight. So thank you and have a good weekend.
Thank you.
Thank you. Bye.
Hi, Professor, I had a question.
Yeah.
So I remember in the first class I asked about rate of convergence and probability.
Mm-hmm.
For convergence and distribution, are we also sometimes interested in the rate of convergence?
Yeah, that's a very good question. Yeah, for convergence, yeah, actually, let me share my screen again. I just stopped sharing. So
I was thinking about it in terms of the CLT and like maybe what the rate of convergence depends on, maybe the second derivative.
It's actually the root n. It's actually the root n, because the root n, as I say, is a stabilizer. It stabilizes the diminishing effect, right? So that's actually about how fast this xn bar minus mu goes down to 0. You need to stabilize by that amount to give it a stable asymptotic distribution. So as we see that here it's root n, but sometimes the thing goes down faster. We need to multiply this by n. We'll see that. So we will multiply that by n. So that's an n rate. Yeah. So the rate is actually in here. Yeah.
Okay. So it's related to this. Okay. All right.
Yeah.
Makes sense.
Okay.
All right. Thank you.
Thank you.
Yeah.
Okay. So yeah, I'll stop the recording for today.